Okay, guys, well, it is 1 o'clock, I think, so I'm gonna go ahead and get started here. Um, Hope you guys are all doing okay. I hope you're doing better than I am. I'm still getting over this cold this week. It's been definitely a difficult week, because I picked it up right before the week started, so I'm kind of going without a break here, but I'll rest up this weekend. I'm pretty sure next week I'll be much better. A couple of announcements. I am gonna tickle you with an extra homework this week, so on Saturday, there's an assignment due by midnight, and this morning I emailed you out a bunch of hints for that homework. So if you look at your Canvas email today, you'll see a bunch of hints there. If you don't want to use those hints, you don't have to. I mean, certainly trying them without the hints would be reasonable. But just so you know, there are some hints in Canvas for you. If you need some help with that assignment. The other thing I'm gonna do is have some extra office hours here because of the homework. So I have my hours tonight. Not sure how coherent I'll be by this evening, but I'm gonna try this evening to have some office hours. And then I think by tomorrow I'll be feeling much better. I don't have to teach at all during the day, so I'll try to rest up for some evening office hours. Both nights, starting at 8 o'clock. And then on Saturday, I don't normally ever have office hours, but this Saturday I will, because of the homework that's due. And, so I'll have hours from 4 to 6, and then again from 8 to 10. As always, these can be in person or in Zoom, whatever's better for you. But feel free to stop by if you have questions on the homework. So that's for Saturday. And then quick turnaround here, there is going to be a homework due on Tuesday as well. The one for Tuesday has 5 problems on it. It's not very long either. Both of them, I could have just put them all together into one, but I actually think this would be better to break it into 2 assignments. So let's do it that way. On the homework for Tuesday, there will be a video notes section for you to write notes out, and it will be for the proof of this theorem. I'm not going to prove this one in class. Instead, I'm going to let you watch my video on that, along with the 60,000 other people who have watched it on my YouTube channel. So anyway, that's going to be for you for next Tuesday. Over the weekend, I also plan to get a review packet together for our third midterm. Our third midterm is 2 weeks from today. So probably that week before the exam on Monday and Wednesday, like always, I'll have some review sessions. And there's already a sample test in that folder, but I'll throw in a review packet and some extra problems for you guys as well to practice on. But that'll be coming up just 2 weeks from today. We do have an exam, and that will cover pretty much starting from uniform continuity all the way through derivative and the first part of chapter 6. We're going to actually start chapter 6 today. So there'll be a little bit of that also on the test coming up 2 weeks from now. Okay. Does anybody have any questions about any of that? Okay. If not, I just wanted to recap this Taylor's theorem again. It really is one of the most important theorems in the chapter on differentiation. It's kind of a generalization of the mean value theorem. I think I mentioned on Tuesday that if you take n actually equal to 0, then you essentially recover the mean value theorem from the Taylor's theorem. So that's just something to keep in mind. I guess it says n is a natural number. There's no reason why n can't be 0 as well. It would work. It would make this whole statement would totally apply to that situation as well. If n was 0, then you would stop with f being continuous and f prime existing, right? Which is the usual assumptions of the mean value theorem. And then the rest of the theorem would follow according to the statement here. So it's actually, to be more precise, I'm sure I copied it straight from the book, but you could allow n to be 0 as well. Okay? So this is the Taylor theorem. Remember, the idea behind this is to try to approximate a function f of x using a polynomial. Now, of course, we can do that. This Pn of x, this is called the nth Taylor polynomial. So the idea here is to approximate f of x with this polynomial. The cool thing about this polynomial is that it agrees with f up through the first n derivatives of f, so at x naught. So just recall here that if I take k derivatives of f at x naught, that will agree with what I would get if I take k derivatives of the Taylor polynomial at x naught. And this is for k equal to 0, 1, 2, ... all the way up to n. So it agrees up through n, like so. Okay, however, well, the idea is that polynomials are much nicer to evaluate, draw pictures of, find roots of, take derivatives of, and so on. Basically, a lot of mathematical things that we can do are much nicer to do with polynomials. So we would like to approximate f of x by this Taylor polynomial. But what we really need to learn, and what we really need to know, and that's the power of this theorem, is in how much error is there? What is the error? And you can see that that's the difference between, so you can see it here, Rn of x, which I'm calling the remainder term or the error term, is just f of x minus Pn of x. So we figure out what the error term is by subtracting these two things. Now, the bad news about this, though, is we usually don't know exactly what Rn of x is. How come? Because if you look at what the remainder term is, there is a c in it, and that c comes from the theorem. There exists a c in between x and x naught, but we don't know what it is. Actually, guys, if we knew what c was, we would be able to evaluate this remainder term precisely, and then we would know precisely what the error was between f of x and the Taylor polynomial. Trouble is, we don't normally know precisely what this is, and instead what we have to settle for is a bound, some kind of a worst case scenario, or an upper bound on the error. So that's how we have to use this theorem. We can use the theorem to get an upper bound on what the error or the remainder term is in this representation of f of x. Okay, so again, the proof for this Taylor's theorem, see homework number 14. There's a video for you to watch. It's half hour or something like that. Yeah.
Does it make sense for the remainder to be 0? Like, is that ever?
It could be. Yeah, the remainder could be 0. For example, if you plug in Rn of x naught, then evaluating x naught, where you have an x here, this would become 0, and you'd have no remainder. And that would just mean that your polynomial and your original function f exactly agree at that particular value. Which actually makes sense, doesn't it? Because we've already made this point that the polynomial will agree with the function at x naught. Not just agree with the function, but agree with its derivative and its second derivative and its third derivative and so on. So that's sort of the power of that result. Yeah. So you can look at this and kind of think, what kind of things would make this remainder larger? What kind of things would make it smaller? Stuff like that. So so the proof, we're not going to do that, but I will make a couple of remarks. And one is, if n is larger, then the remainder function Rn of x tends to get smaller. And you can all see why, can't you? If you look at this Rn of x here, the bigger n is, the bigger my denominator is here. Does everybody see this n plus 1 factorial? Right, so that's gonna create a smaller remainder term. And this, of course, makes sense. If you're willing to put in the work to evaluate a larger value of n for your Taylor polynomial, you should expect that the remainder would get smaller, the error would get smaller. So that's one thing. Another thing that would make your error smaller would be if the x value was close to the x naught value, right? So in other words, make this x minus x naught smaller. So if x is closer to x naught, then Rn of x also tends to get smaller. Okay, so those are a couple of just qualitative behaviors that you would expect to have here. Okay, so with that in mind, I'd like to do maybe a couple of examples of how we could apply the Taylor's theorem. As I said, I'll save the proof. I'm not going to do the proof today, but we'll do some examples anyway. Just put this over here. Let's do some examples of this theorem. So here's, I'll just actually call these applications. Just going to do a couple of them for you, just so you can kind of see what this is used for. One, let's try to prove that the cosine of x is always greater than or equal to 1 minus x squared over 2. So this would be for all x in R. Okay. So we're going to try and do this as an application. So for the proof of this, what we can think about is what I see on the right-hand side looks like a polynomial. So it appears that we are comparing a function f of x with a polynomial that is associated with that. So let's set up our f of x to be the cosine of x. And let's try and calculate a Taylor polynomial for it. What value of n, which Taylor polynomial are you tempted to work with here based on the right-hand side? 2, right? It looks like a quadratic function. So that would be n equals 2. So I'm kind of tempted to let n equal 2. And let's write down the Taylor polynomial. Now, when I write down the Taylor polynomial, I'm not using the theorem yet. Right? I'm not using the theorem until I actually look at the remainder. So then let's work out P2 of x. Okay. Now P2 of x, as we know, that's just, oh, we also need an x naught value. I also have to have a base point, as it's sometimes called, for my polynomial. Let's come back up here. Let n equal 2, and what do you think I'm going to let x naught be? Looking at the right-hand side, this is just x squared. It's not like x minus x naught squared. So I'm guessing that the x naught is actually 0 here. So let's write down the second Taylor polynomial centered at x naught equals 0. So that would be f of 0 plus f prime of 0 times the quantity x minus 0 plus f double prime of 0 over 2 factorial times x minus 0 squared. And again, so far I'm not using Taylor's theorem. I'm just simply writing down the second Taylor polynomial. Now, before I plug anything into that, let me take a couple of derivatives of f. So the derivative of cosine, as we know from calculus, that's negative sine. And then f double prime would be negative cosine. And I'm going to need to evaluate these at 0. Let's just go ahead and do evaluation here at x equals 0 because we're plugging in 0 into these derivatives. So obviously, when I plug in 0 into sine, I just get 0. When I plug 0 into cosine, I get 1, but we do have a minus sign on that. So we end up getting a -1 there. And so now plugging those values in, let's refine what our P2 of x is. Oh, I also need to evaluate f of x, which is cosine of x. I also need to evaluate that at 0. So that just gives me cosine of 0, which is just 1. Okay, so I've evaluated my function and its first two derivatives at 0. Let's just plug everything in. So f of 0 was 1. F prime of 0 is 0, so the middle term will go away. F double prime of 0 is -1. So we get -1 over 2 factorial is just 2 times x squared. So guys, in fact, as you can see here, the right-hand side of my inequality is just my second Taylor polynomial, right? It is just my second Taylor polynomial. They are exactly the same thing, and we're just trying to show that the Taylor polynomial P2 of x always underestimates the cosine of x. It's always less than or equal to the cosine of x. So I'm going to now look at my remainder term and calculate that. So we have R2 of x equals, it'll be a 3 factorial on the bottom. I actually have to take 3 derivatives of this function. Let's go up here and do the third derivative of f evaluated at x. So that's going to be sine of x. I'm going to evaluate that at x equals 0, and it's going to give me. Oh, I'm not evaluating that at 0. I'm taking the third derivative of f, and it's being evaluated at c. C is a number that's between 0 and x. Okay, so I'm evaluating this at c, and that gives me sine of c. Right? So I plug that in on top here, I have sine of c. And then this becomes x cubed. So the power on the remainder term, the n was 2, so the n plus 1 becomes 3. So here is my remainder term. And what I claim is, what do I need to prove about this remainder term? This is my original f of x. This turned out to be 1 minus x squared over 2, right? I'm trying to prove that f of x is greater than or equal to Pn of x, which means I need to prove what about the remainder term? Careful. So if this is going to be greater than this, what's that tell you about r? Positive. That's all I'm looking for. Yeah, it's positive. I need to prove that Rn of x, I need to prove that this is always greater than or equal to 0. Make sense? Okay. Well, I actually have some doubts about that. Because the sine function, as you know, it oscillates positive, negative, and I could see if that was negative while the x was positive, this might come out negative. So it's a little unclear. So what I'm going to do is I'm going to analyze this for different values of, or different ranges of x values. So let's just take a look here. If, I'm going to make a couple of bullet points. If x is between 0 and pi, let's just start with that. I'm going to just take this in baby steps, guys. If x is between 0 and pi, then would everybody agree that this is positive? Because sine of it, if you remember the sine graph, so let's just forget my claim for a moment. Sorry, no claim here. So if we just remember our sine graph goes from 0 to pi like that, and 2 pi, negative pi. So this is sine of x as a function of x. So if x is between 0 and pi, let's put this down here. If x is between 0 and pi, then sine of c will, remember, c is between 0 and x. So if c is between 0 and x, then it will certainly be in this same interval, right? So sine of c would be greater than 0. So r sub 2 of x would be positive, and we're happy about that. We want that to be the case. What about if x was between negative pi and 0? Well, now I have a negative number. I cube that negative number and it stays negative. But what about the sine of c? Now c is between 0 and some negative value of x, right? Well, on that interval from 0 to some negative value of x over here, my sine function is also negative again, right? So in this interval, sine of c is less than 0. And so R2 of x, again, is actually greater than 0. Okay? So for x in the interval negative pi to pi, R2 of x is positive, and so f of x, which is the cosine of x, is greater than or equal to 1 minus x squared over 2. I have proved my claim, at least for x's that are between negative pi over 2 and pi over 2. What about even larger values of x? So if x was bigger than pi here, then I get a little nervous because if x is bigger than pi, sine of c could be negative. I say could be. Remember, c is between 0 and whatever x is. So if x is over here, then there are values of c potentially between 0 and x where the sine function is positive. There's other values where it's negative. We just don't know. This is the whole downfall of that theorem, is we don't know what c is, right? So we're not really sure. But the point is that if x is bigger than pi, there's a potential for this to be negative. Now, we actually know that it can't be. We know that it can't be because we're proving this. We're proving that f of x is greater than or equal to p2 of x. So it actually must be that this is positive. But I can't prove it directly by just using this expression, because depending on where c is, the sine of c could be positive and could be negative now. So you know what I'm going to do now? You know what I'm going to do for x's that are outside of that interval from negative pi over 2 to pi over 2? For x's that have an absolute value that's bigger than pi, so we're talking about the rest of the real number line, I'm going to abandon the Taylor's theorem completely. I'm not going to try to apply it, because the problem with applying the Taylor's theorem for x's that are in this interval, as I already said, we cannot control this c, but we're not going to know whether sine of c is positive or negative, and we really would need to be able to convince ourselves that it was positive in order to know that this remainder is positive. We can't do that. So I'm going to completely abandon Taylor's theorem. I'm not even going to look at the remainder. I'm just going to go back to here. If I put in a number that's more than 3 in for x, so you plug in, what kind of x values am I plugging in now? I'm plugging in x values that are at least 3.14. By the time you square them, you're looking at 9 and change or larger. Cut that in half, you're still looking at about 4.5 or larger. If you take 1 minus something that's at least 4.5, you get negative 3.5. And I know that cosine of x is between -1 and 1. So it will certainly still be true. So what we can do here is we can say then we can just directly analyze it. then if I look at 1 minus x squared over 2, I think I said it would be less than or equal to about 3.5. Just to be comfortable and keep the numbers nice, I'll just say less than or equal to -3. Okay, which is obviously less than the cosine of x. So we're not using the remainder theorem, we're not using Taylor's theorem, sorry, at all, to prove that this inequality is true for the x's that are far away from 0. It makes sense, right? Because the Taylor polynomial is, this theorem is true for all values of x and x naught, but if x is far away from x naught, we can't really control this remainder so much. We don't have as much information about it, so it's, in this case, better to just abandon the theorem and just prove it separately, as you can see right here. So in all three cases, whether x is between 0 and pi, whether it's between -pi and 0, or whether it has an absolute value that's greater than pi, in all of those cases, we get the inequality to be true. Everybody okay? Yeah, Lindsay?
So Jennifer, how did we get the x naught to be 0?
We chose that. We chose it to be 0. We're allowed to do that because we're using this theorem over here. It says, all right, we've got our cosine function, right? It's got all the, its derivatives are all continuous and so on. And it just says, let x naught be in some interval. In this case, my interval AB is really, it's the whole real number line effectively. So yeah, that's essentially our choice as to what the x naught is going to be. Yeah. Okay, let's do one more practice problem. And are there any questions on that? So far, so good? Okay, let's do one more. For this next one, call this application number 2, I would like to approximate. See, I'm not going to spend too long on this. This is not really a class that's focused on applications. Right? This kind of stuff, approximation theory and inequalities, would generally be done in another class. But I just want to show you the power of the theorem, at least this one time. Let's approximate E with an error of less than 10 to the -5. Okay. So now what we can do is we can approximate the E by using a Taylor polynomial, but we need to do it with a sufficiently large value of n so that this remainder part is guaranteed to be less than 10 to the -5 for whatever the C is and whatever the x is in this expression. Okay? Of course, to use the theorem, I have to have a function. Does anybody want to suggest what function I would be defining here? E, what's that? E to the x. Yeah, exactly. I would just use e to the x. Right? So we'll just take our e to the x function. That sounds good. And in this problem, we don't know what n is supposed to be. So let's write down just in general what the nth Taylor polynomial would be so what would be the x naught value that we maybe would want to use here? You have to be careful. It's tempting to say I'm going to let x naught equal 1 because then I can just plug it in and I get e, which is what I'm interested in. But if x naught is equal to 1, look at what the Taylor polynomial is going to require of you. It's going to require you to evaluate e to the 1 right away, which is the thing that we're trying to approximate, right? So we're actually kind of in a catch-22 if we chose x naught equal to 1. So they should have explained this in your basic calculus classes that you usually want to choose x naught to be a number that you can easily plug in to your function and get a value, right? So whether it's a trig function or an exponential function or something, that's the idea. And it should be a value of x naught that's easy to plug in and which is close to the value of x that you actually care about. Now, with that in mind, does anybody want to suggest something? What is the ln of one? Let's just do 0. Yeah, so that's exactly right, yeah. So we'll just use 0 here. And that's exactly what I'm gonna do. So my nth Taylor polynomial will just be, and by the way, all of the derivatives of e to the x are just e to the x, right? So when I plug 0 into e to the x, I just get 1. So all of those f of x's are just gonna turn into 1s. So I'll have a 1 and then plus x. Again, x naught is just 0. So, and then we'll get x squared over 2 factorial, x cubed over 3 factorial, and da 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 da. The last one would be x to the n over n factorial. So this becomes your nth Taylor polynomial. And so if we plug in 1 into that, so I'm now going to plug in the x that I actually want to evaluate e for. So Pn of 1 would be 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial dot 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 plus 1 to the n over n factorial. And so that's just 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus dot 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 plus 1 over n factorial. So for any n that we might choose, this is our approximation for e to the first power. That is the approximation we're going to have. But what we need to know is how good is that approximation? It will be hopefully a better approximation the larger n is. So what we need here is we want the absolute value of the remainder, which is the error term, to be less than 10 to the negative 5. Let's figure out what that remainder term would be. Again, the derivative of e to the x as many times as we need is just e to the x, and we're going to evaluate that at c. So that is absolute of e to the c times x to the n plus 1 all over n plus 1 factorial. This is all supposed to be set less than 10 to the negative 5. Okay. And the problem, as usual, is that we don't know what c is. What do we know about c, though? It exists between 0 and 1. Okay? So where c belongs to the interval from 0 to 1. So what you want to do on something like this, guys, is you want to take kind of a, well, let me rearrange the equation just a little bit. E to the c, we don't really need these absolute value bars, so I'll just say that is, one more time here if you don't mind. That is e to the c times, now we're going to be plugging in 1 for x. Right, we've already plugged in 1 over here and over here, so we're going to be plugging in 1 for x. So that's 1 to the n plus 1 over n plus 1 factorial. See, we don't need the absolute value bars. Less than or equal to n plus 1 fact. Less than 10 to the negative 5. Okay, so this is equivalent to e to the c divided by 10 to the 5th, I guess. Less than n plus 1 factorial. That's what we would have. And the question is, what are we going to do with this estimate here? Because we don't know what c is. We do know that it's between 0 and 1. So this could be e to the 0, or it could be e to the first, or something in between. That's basically the point. So what would be the worst case scenario. Like, the worst case scenario, because this is kind of the error here, or this, or you can think about it this side here. The worst case scenario is when this is as big as possible. Right? When the remainder is as big as possible. So the worst case scenario on this expression would be if C is actually 1 or approaching 1. Right? So in other words, I'm gonna kind of think about backwards scratch work again. If I put in a 1 for C, this is gonna kind of give me a worst case scenario. If E over 10 to the 5th is less than n plus 1 factorial, then E to the C over 10 to the 5th would certainly be less than n plus 1 factorial. That's because this numerator, right, is smaller than this numerator. Guys, C is less than 1. C is less than 1, so E to the C is less than E to the 1. So here's E to the 1. If that's less than n plus 1 factorial, then this will be less than n plus 1 factorial. And this goes to here, goes to here, goes to here, right? It's kind of like scratch work that we're gonna think about running in a backwards direction. You can kind of think about it that way.
How did the exponent become positive?
The exponent. Pardon?
So, yeah.
Oh, this?
Yeah, you switched.
Well, when I moved it to the other side of the equation. Oh, did I screw that up? I probably did.
Would be a negative.
Yep. That,
Okay.
actually, it would have made more sense for me to just leave it on the other side. But yeah, that's exactly right. That should be still 10 to the negative 5. What I could do, I think what I meant to do was flip it to the numerator. So this would be in the numerator, 10,000 times E less than n plus 1 factorial. Yeah, sorry about that. Okay. Thank you. So there's your corrected statement, and 10,000 times E would then be a lower bound for your n plus 1 factorial. Now, you say, okay, I want to solve for n. To solve for what n needs to be, I have to evaluate 10,000 times E. Oh, but wait a minute, that's what we're trying to approximate what E is. So I can't just decide to go to my calculator and put in E right here, because that's the number we're trying to approximate. But what we do know is that E is between 2 and 3, right? So what we could do is we could say, well, let's just up it to 3. So as long as n plus 1 factorial is greater than 30,000, right? And so I'm replacing 10,000 E with 10,000 times 3. That will be larger. And so as long as n plus 1 factorial is greater than 30,000, it'll be greater than whatever this is. So then you can now solve for n by using a calculator, which I did, and I got 8, actually. So this requires n to be at least 8. You can check it out. Calculate 8 factorial, calculate 9 factorial, and you'll see that 9 factorial is the first value that's larger than 30,000. Nobody said you had to find the best value. If you wanted to take n to be 10 or 11 or 12, that'd be fine. But you'd be getting an even better approximation if you did that, right? So E is approximately 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 8 factorial. And I actually calculated this. This side on the right hand side is approximately 2.7182787. And if you work out what E actually is, the first few digits of E, 2.718281828. And so these should agree up to within 10 to the negative 5. If you subtract them, If you subtract these from each other, you're gonna get 0.0000 something. Yeah, so that's 10 to the negative 5. Okay, anyway, this isn't really what this class is so much about. The actual applications and stuff like this, you'd see those probably elsewhere. But it's just kind of nice to see that these results that we're approving do have, realistic applications. Questions? So the main thing is, we don't know what C is. So you have to kind of look at like, what's the range of values of C and what would be like worst case scenario? The biggest possible remainder would also align with the biggest error that you could have. So we've chosen a C value of 1 right here. I've replaced e to the C with e to the 1, knowing that that will make my remainder term as big as it could be and give me a worst case scenario for the error. Okay, is everybody okay with that? Questions? Okay, so again, I'm gonna leave it at that for Taylor's theorem because I'm gonna let you guys watch the proof. When you do watch the proof, please, I'll have you take notes on it and submit those with your homework for next Tuesday. And if you have questions on the proof as you're watching it, feel free to, well, you can ask me or you can put the questions into the YouTube. And then you'll allow anybody to answer. If you want to do it that way too. Okay, well, the last thing I want to do with this chapter is just that group work that I passed it out on Tuesday. And then we didn't have time to actually do it. So I think, was there anybody else who didn't get this group work from the other day? Oh, sorry, that's the wrong one. This is the right one. Or does anybody need a copy of this group work from Tuesday, or did y'all bring it with you? You all brought it with you? Okay, great. Why don't you grab your partners and come on up and work on this? I would recommend that you do problem number 2 first, because I think that'll go a little quicker. And then at least with problem 1, if you just kind of get the idea behind it, I think that will be good enough for now. So let's take a little bit of time and let you guys, this is gonna be good. I'll rest my voice a little bit too. Bring you guys on up here, and this is just practice with derivatives, really. That's what it's all about. So go ahead. Come on down. Come on down. There's some markers up here on my table. If you want to grab some of those as well, I'll get out of the way. And start with problem 2. Come on down. Everybody should work with at least 2 other people, maybe 3. 2 to 3 people would be great. And take turns with those markers as always. And I'll be here to give you a hand. All right. It's very quiet.
Dr. Annie, can I see the board?
What do you want to see?
I just want to see the board. I just want
Okay.
to see what people doing it.
See
Yeah.
what people are doing?
Yeah.
Okay. Sounds good. I'll set you right here.
I can't really see the board from here though.
Okay. Let me see what I can do. I'll just do it like this, okay?
Yeah, honestly, yeah, that works.
Okay, perfect.
Thank you.
Okay. This is supposed to be C plus H. Oh, I see, you're plugging in this, I'm sorry, okay, yeah, sounds good, that sounds good, looks really good, actually. Okay. Good job there, guys, good start.
Somehow got put in my book.
Do you need another copy?
No, I'm just saying that got put in my book, so I just set it aside.
Oh, okay, yeah, I did that by mistake. Nice. Looks good. Looks good.
Well, we know that prime zero is this, so that's the equal zero. And that solves this as well, because that's what we're given.
I don't think.
Zero.
Starting with the definition of f C.
Now, I think what we can do is, we know H is trying to be realistic, H is zero. Now.
Now, the thing is, if you plug in zero into that, then you lose the C completely everywhere. So if you look at what we're trying to prove here, we don't want the C to be completely gone. That's part of what we're proving. So this is fine. This would be fine, to put in zero on both sides. That goes C. So you're just plugging in zero for. So if you're gonna evaluate f prime of zero, then you're using C equals zero, okay. And f of zero was given as 1, so yeah, so this would be right, this would be correct. But we've lost the C. So I'm gonna suggest we don't do that, let's not plug in C. Why don't you go ahead and put that up there, Robert, and then let's stare at it. I always have to write it down and then stare at it. Looks good. Remember that f of C is just a constant.
We don't need to take.
Or what, we can pull it out.
Yeah.
Yeah, we pull it out. Let's see what happens if you do that. Only.
I don't know, it's like, it's.
I started off with an H, but I think it's a different variable. That's what I did.
That is totally correct, but the problem is. So if we look at what we're trying to prove.
I think you need
What
one
we're trying to
more.
prove is something about having finite. So, I kind of like what you have here, because you still have the abstract of C and then you have this thing here. Work on this fraction right here. That might be a better way to go rather than actually plugging a number into it. Finding for that C arbitrary.
Okay, then that's not move that out. And this is. Right, C, if C is zero.
Oh, nice.
If C is zero, that's H minus. If C is zero.
Yeah, this is just a constant. So it can be pulled out of the limit
So that's
in
just.
front, which is what we did here. And then what you're left with is really just the derivative.
Check.
Oh, I just made it right here.
This should be, this is a zero, yeah, f prime is zero, yeah, that's just the f prime is zero. So it works.
I did, it looked a little rude.
So it works.
That's why I was
Well,
saying, we're used to that H, but I was.
yeah, the trick is to factor the f of C here in there.
Usually we
And then this fraction becomes just f prime of zero. And f of C is just a constant.
Sorry, how that
Straight down. That's how it works. Let's see, did you guys get anywhere?
Unless it does.
the X, I don't know what the X is here. This X right here.
I said. If you do it directly, like.
But there's also no Y in there.
Oh, maybe I meant. There's one.
Well, that's just the, yeah, that's just the general property that you're using here.
Oh, and that's where you're supposed to use it.
Let's just work on, let's just work on this fractal, let's not get so complicated. Take this fractal, can you do anything with that? This is,
Yeah.
yes, that is exactly right. Good job. Any questions on that? All right, good job, good job. Try and see if you can do problem one. Okay, perfect. Just do some algebra on that fraction.
Maybe we can do this.
You feel pretty good about this?
Maybe, oh, it maybe it's.
Maybe Amber with a quick rundown?
Yeah.
Okay, sounds good, sounds good. You guys are you guys solid on this? Yeah. It feels okay, so you distract, the key step is FOC is a constant factor. And then this one is just F prime. So that's all that you figured it out. I got.
That's a weird one. Chairs.
Okay, why don't you can erase that and try and do problem one. Oh, take a picture first, yeah, for sure. Okay.
Oh, because I want to take.
Or not the product now.
Yeah. And can see that looks a lot better now.
Okay.
Yeah.
Said. Or.
Yeah.
This is a subtraction sign, sorry. It's basically this, it's nothing, and then if C was 0, then it would just be F of H plus F of 0 over H, and we can just replace that to be F of 0.
Oh, yeah.
You got it right. There you go.
Remember that FOC is a constant. It's a constant there, and that's its expression you have.
He's saying.
So good. This is not F prime of C divided by G prime of C. This is F over G prime. So it's the quotient. See, I would write it as F of. I was just trying to get exactly how I have it on the hand. F over G prime. Of C. And that is not the same thing as F prime of C over G prime of C. So I have to write it like that. Yeah. Okay, let's factor out the F of C because it's a constant. No, this is just F of C. Let's factor it out.
No.
Okay, so this is just a constant, so I can pull it outside of the limit, right? And if I look at what I'm being asked to prove that F prime of C is equal to F prime of 0 times F of C. So here's the F of C right there.
Oh, yeah.
Doing F of C here. So I just need to convince myself that this here is actually F of 0. I'm sorry, F prime of 0. Yeah, so let's just see, well, what would F prime of 0 be? Factor the limit as H goes to 0 of what, F of H minus F of 0 divided by H minus 0.
Well, it's kind of like you don't work there.
Derivative. Prime of zero by definition is just a limit of this difference quotient right here. Well, with that, it's exactly what you have here, because they gave you f of zero is one, so you're good to go. You bet.
It is the vendor's friend.
Let's see if we can prove the quotient rule.
Okay. Work back, wait.
The trick of it's low times high.
I know, really knows where it's at. Yeah, right, it's
Yeah.
super meaningless.
So far, we've been coming along.
We have to add.
Yeah, that's for sure. That's probably something. Yeah, I think you could, if you wanted, you could do.
But I guess you have to
Might be
remember
slightly
slightly
easier, I'm not sure. Do F of C, G of C, G of C. It shouldn't really make a difference though, but it would be worth considering that because you see the F, C, D here.
Yeah. FOC times.
Just the thought.
Never.
I think it probably works either way.
I learned it in high school.
Oh, yeah, that's great.
I couldn't do it. I couldn't even do like, you go
Yeah.
Here we are, math major.
Okay. I'm trying to keep you guys motivated here.
Well, limit and x goes to C.
Because.
Yeah.
But in, I think we just put in division would be
G of C. All over x minus C.
Oh,
Now,
that's-
and this is just f of x over g of x, this is just f of c over g of c. So why don't you start working on those fractions, okay?
divide them.
Yeah.
Yeah, just.
No, this is not f prime of c over g prime of c.
That is the work.
Right, this is, I'm not just dividing these. I have to, first of all, let's write this out limit.
And they have a lot of.
C over G.
And how does that derivative limit work? Well, we have x minus c on the bottom. On the top, we have this difference quotient.
Right.
Okay, and when I write f over g of x, that means f of x over g. So this is f of x over.
Oh.
Try to get one more step for you, and then I'm gonna let you take it there. So this is f of x over g of x minus f of c over g of c. And then over x minus c. But now I want you to do some algebra, on those fractions.
Yeah.
Okay, so we got the cross multiplying going on.
Right, it stays on the bottom?
Yep.
Okay.
Yep, you have it perfect.
Now.
Now, remember that on the right-hand side, you ultimately wanna see, so like I already see a g of c here.
Right, but I want.
I don't see the f prime of c. F prime of c would be like a limit of f of x minus f of c over x minus c.
Yeah.
It's a little, so I don't know if you remember the proof of the product. Or we did
Yeah.
the multiplication, not off the top, no, and that's okay. But what we had to do with the product rule is we had to add and subtract the same thing in the expression so that we could group things together that look more like different quotients.
So answer this.
I'm gonna suggest we add and subtract the same thing. And make this a little longer initially, and then make it shorter. And what you're gonna put here is not making a derivative, so you're just gonna put
GFC.
stuff involving the method.
Yeah.
Yeah.
Over GFX, GFC.
So no primes, no primes on the right hand side, just F's and G's, or X's or C's.
Oh, yeah.
Basically, the.
I'll let you think about
I'm
it.
missing
Let you think about
squares involved?
it. No square.
Okay.
No
Squares involved.
No squares, no squares. Okay.
Oh, wow.
It's looking really good. Yeah, I think you're getting it. How are you guys coming?
Yeah, that's what I was saying. Okay.
Hit a little speed bump here. Let's see.
But I get that's what you're trying to say, I just didn't know if this.
I think you can just say that.
So this is the definition.
Wow. Grouping.
I don't know.
That
what
one.
What is this? Equals the limited H to zero. F of C plus H over G of C plus H minus F of C over G of C. Right? And what you're going to want to do with this is cross multiply, basically to simplify this, cross multiply the fractions and simplify. Okay? Let's see if that brings it up a little. Yeah.
Took out the minus.
Uh-huh. Yes. Yeah, it's basically a future mark, so G is a differentiable function for us to even be able to do this problem.
Dr. Hannon,
Automatically continuous.
The reason why
If it's continuous, then we know that the limit of x is G of C. And that's a concept that you can really pull out of the limit.
Dr. Hannon,
Really. That's basically it. They're almost done, because this is just F prime of C. This is just G prime of C.
No, we don't have
Where you have
because they're both
I
together.
D
It
of
separates
all the square.
And then
That's good.
Yeah, and then those will, that will cross out on that one.
Nice. Now, this is going to be,
Yeah.
I can see that when I plug in 0 for H on the bottom, I'm gonna get my G of C squared, right?
Yeah, but we need
then
that
in the
here.
rest of what I have, I don't have, like, I'm trying to get these guys to show up. Because on the right hand side of my
No, I
formula,
guess
I
you're
need
fine.
to have.
Yeah.
So in particular, there's a minus sign here, there's a minus sign here. And in your numerator,
Right?
no minus sign.
This one we can't.
So one trick you need to think about is there a?
No, but if you're
actually, this should be a-
splitting it, you
It should be a minus.
can. Splitting this. I know, but this doesn't.
Okay,
Don't add.
but it's still not set up for you to like factor and get this expression
Get rid of
here
the.
or this. So the trick to this is the key step, and we have to do something like this for the product rule as well, which is that we need to add and subtract the same thing on the top. And I think what would work, I'm gonna recommend that you check me in on this, is if we just add and subtract F of C, G of C. And then let's take the 4 terms that are upstairs and group them into 2 groups of 2. One of which hopefully will give you the F prime of C coming out of it, and the other of which hopefully will give you the B prime of C. In terms of this trick? Yeah, it's, I mean, I would say always, since we don't use this trick very often. But yeah, in this case, I just kind of want to mix and match what I have. I'm not saying this is the only thing that would work, but it's the easiest thing that I can think of that will allow me to give me a little bit more meat on the bone that I can create these 2 terms out of. So that's kind of the motivation. So I think, for example, you probably want to combine the first and last term, the far outer terms together, and then I think you're gonna want to combine those. That's right. I think that's how this is gonna work out. Okay.
The guy on Reddit.
X minus C ten.
You guys okay? Where are we at?
It's kind of got lost now.
Made a common denominator. Do you guys have that? This is all correct. Okay, but the next step is a tricky one. And what it is get a better marker here.
Never mind.
The next step is really a key step.
You're gonna want the. So
So the denominator is this. The numerator, I have G of C, F of X. And I have, I'm gonna put it over here, G of X, F of C. The trick to this is
So maybe the
to
one that's
subtract something
this.
that will allow me to create these kinds of things. So I see, for example, I have F
Oh,
of
I see what you're
X,
saying,
Yeah.
yeah.
but I don't have an F
those
of
two
C.
together. Okay, so let's change the way.
That's also, that I can back to this G of C. So I'm gonna put in G of C, F of X.
I was taking 3 hours.
Again, why am I doing that? Because then I can, just with these first two terms, I can factor G of C. And then I'll have, when I factor that out, I'll have F of X minus F of C, that's a plus.
And then you take out.
Once I factor that G of C, I'll have F of X minus F of C over X minus X. And then I'm gonna do plus G of C, F of C, and I'm gonna combine these two in a similar fashion.
Okay.
That's the trick.
Okay, thank you.
You're welcome. Oh, good, you guys got the.
Yeah.
This-
We were trying to factor these.
Oh.
We had this, but we were trying, we didn't know.
It's okay.
And now we're back.
You're back on
Now we're
track.
back.
It's looking good, looking good. Does anybody need help? Did you guys get it all figured out? Okay. You guys can take a little bit of a break if you want. Sort of do our 10-minute break and then we're gonna start integration. Yay. Is it working? Nice. Nice, nice, nice. That goes to 0 and you get exactly this closure row. Looks great. My only complaint is you can have equal signs.
One of my friends.
And we should still have a limit on it. That counts. But if that's the crux of it, absolutely.
Closes it, he just gives it to the.
Did it work out?
He thinks so.
Yeah,
Yeah, you're getting that. You see-
I want that.
Still, still a back right underneath there, phone,
Yeah.
and then you kind of split.
But I
Do a new
made-
one here.
Now, that's the only thing.
I make a new one here that I also have. to put in. This is actually extracted from a raw order, so you normally you have G of X minus G of C. Here you have G of C minus G of X. You can fix that by the fact that it's plus, you make that equal minus.
Yay! We figured it
This is just G of C times F prime of C minus F of C. times G prime of C. And it's all over, we forgot the G of X, G of C here. And there's more sense. You guys get it?
Yeah, I know, like what you're.
Hey, guys, let's take a little break, until maybe close to 2:20 would be fine. Give you, 7 or 8 minutes anyway to stretch your legs if you'd like, and then we'll start up again soon. Everybody finished?
Yeah.
Did you guys finish over here?
Yeah.
You know what I really like? At the left side.
Yeah, that's what I'm.
So well, nicely structured, right? It's not real like all over the place. You have
I
it
mean,
very.
we missed one of the equals that could have been there.
Ah. But for the most part, this looks really, really good. So, nice job, nice job. Awesome.
Yeah, right, so.
Was like.
Would you mind erasing
Yeah.
that for me? I really appreciate it.
If I ask him, who's teaching?
Casper,
In the summer?
I don't know, but Casper's teaching both sessions next semester.
Oh, God's.
I know, I gotta pass.
Do you know when they come out this summer?
I checked on the bulletin board by the math office, but I don't know if he has someone who wants to teach it. I know Soto wants to teach it.
Oh, please. Soto would be so nice. Soto would be so nice.
As long as it's not,
I
what's
would
that?
die.
The board.
Bourget?
Or isn't she not?
No, Lady Bourget wouldn't teach it. It'd be Mr. Bourget.
Is he okay?
Dr. Bourget's the worst. Him and Lady Bourget, they're both terrible. You can laugh all you want, but it's true.
I hope so.
The thing is, like, I did the independent study, I was doing, 405 or whatever they are calling that class. now.
Yeah.
I did the independent study with him last year, so we went over all the calculus last year, so. I'm like, I understand how Soto was doing it, but he was also like, we have this really big proof. We need this one, where did this proof come? We need This one, so it's like a rabbit hole that we went down.
See, I love Soto though, because better than training. I thrive.
I did something about adding lesser.
I did. Honestly, if he taught that class like a regular person and he didn't do those pretests, I probably would have failed.
He gave me an incomplete.
That's my biggest
He
flex.
gave me an incomplete. I had to finish with it all.
Period. No, that's my biggest flex. I passed 307 lesser on the first try.
Fast 302 with lesser.
And don't talk to me about the review. I had to take that class like 2 times.
Well, this was dumb, I took it with Lion. First of all, that man, next slide.
Someone was telling me, who told me that?
So literally wanted to cry.
Carly told me that.
And I don't
She
actually.
switched
learn
majors
that.
after him.
Yeah,
She's like, I can't.
and I would go to this. Like, yeah, I read the book.
Gloucester didn't even give us a book for 302. Girl, he didn't even use a book. His notes are so disorganized. He'd be like, oh, what's that? Word? Be like, oh wait, but you
On a
need to
tangent,
hear
I'm
it. I'm
like,
like, oh my god, you're killing me. You know who has the best notes in the entire department? Yeah. Dr. B.
Real. I took hat
We
to
have-
80 with him.
280.
Yeah.
The prettiest notes, the most organized, the easy to
Nice
follow.
writing.
Oh my god.
Why am I even in this class? It's okay though.
I'm an imposter. I don't know what you're talking
I have to. I'm like, but I'm getting this down
I
degree.
agree.
Respectfully.
about. I got 4 weeks. 4 weeks. I'm gonna pass this fucking class. Where to go?
I'm like. I already did do literally my schedule for next year. Looks not too bad. My holiday semester is fall.
My kid is gonna be.
Dude, I walked in and there was a cat on a leash. In front of Nutwood with the dog.
I take my cat.
kinda chilling.
I take my cat on a leash. She loves going. He's a
Cats
Maine Coon
deserve
now.
walks.
He's a Maine Coon though, so he needs to go home. I have 2 new ones now too. The kittens, the ones that I had in December, they're his.
Oh, I wanna make him so bad.
He loves to go outside. I don't think he's full though. It's like half.
That's okay.
He's got the big fur. He's got the face too. But
I always thought my cat was England.
No, it's nice.
he's beautiful, but he's kind of so.
Even though you did that, I didn't
Yeah, yeah, I am.
Dude, he's so big.
No.
So cute. So she's just like.
This is my.
Oh.
Oh.
Yeah. Oh my gosh.
Isn't he so cute? He tries to get it from my sister.
It's my dog. His name's Chicken. That's what's big. It's just a silly little guy. No thoughts behind those eyes.
Nothing going on.
I was like, oh my God. I was like, I have a lot of picture of food. Bread.
I have so many soccer videos, it's not even funny.
It's food, my pet.
Mine is
School.
Mine is whiteboard.
Look at here.
I think of like whiteboards. My
Like, you would say you're some of this level even this.
whiteboards, my kids, and then soccer.
Something weird happened here.
Well.
Yeah, you showed me that the other day, like,
Yeah. So I put
an
in,
idiot.
I replaced H with H minus zero.
Yeah.
Doing that is to just make
That's
it
all it
look like the derivative.
Literally have all boys.
So.
Yeah.
That derivative definition.
He was
there,
supposed to be a girl.
or-
They
Right, I
told me it
wanna
was gonna
make
be a
it
girl.
look like that, so I wanna have. I'm
I had a
supposed
girl
to-
for all of 5
look,
minutes, they looked
yeah.
again and he was fighting, and I was like, that's not a girl.
So F prime is zero.
That's my aunt. She really wants a girl. And she had
It's just
kid, not a girl.
This.
And she had another one, not a girl. Did she have another one?
So I'm trying to make that show up in my.
Okay. Twin?
But we use the H definition.
Oh,
Yeah, no, they 4
I can
times
change
and I
this.
failed 4
I can
times, I
change
was
this
like,
to
I'm
an
done.
H.
The girl's not one.
Done, but then my niece came along.
And I'm okay.
Oh,
Yeah.
that's supposed to be girl.
We'll just have to see it out.
We
Right.
did give girl.
Did have to see.
You did the formula, yes.
Oh, she is so adorable.
F of H.
You replace because H goes to zero and F of zero is one. That's what's given. H goes to zero, right?
Like, she kept fighting with him.
Lines.
Oh, you're gonna fix, that's how my
She
cat
had
works
to
too.
keep her because she hadn't had vaccines or anything.
He's so cute.
Dude,
shut up.
No.
She was just.
I mean, like, I couldn't.
Um,
Got the
That's why I said
fur.
that.
Where did I?
So
The problem is what you're doing right here, 1 minus 1, that's, so H doesn't get
What's that,
turned
my
into
pocket?
a zero.
No, this kid's always been this
After
way.
the very end, when you take.
Not really, actually.
So you can't just, I mean, if I'm gonna plug in what F of H is, if I'm gonna plug in F of zero.
My little Sunday.
Then I would just assume be plugging in a zero.
Four
in the
times.
denominator for this equation, but you can't.
Always hungry, always hungry. There you go.
No,
It's all
so,
the time, but also not even understanding the first one, so.
okay, so this is just,
Sushi?
this is just by definition, we can use an H or an X.
If I could.
This is what you're supposed to get in the answer.
Cat sanctuary.
Problem's asking you to prove
I know how to picture me.
this,
I know how to do
Shot.
so I gotta find out how to make that show up in my derivation. And so this is what that equals, and in your derivation, you have something that's very close to that, you have, I would factor that F of C out of that limit, by the way. So just pull it out, it's a constant. So, you know, you have this, this is given, and all you gotta do is convince yourself that, well, it's the same as that.
If you're a graduate
Because that's
senior.
you look at
you
the same
probably
equals that
already-
Cause I know that 1 is the same as F of 0, and I know that subtracting 0 doesn't change anything. So this is the same as this, this is the F prime
They're the
of
ones who
0.
told me.
For a lot of it and doing what you're.
Check into it.
I'm gonna let you think
I
about it.
mean, F of C is what you pulled out.
Yeah, factor out the F of C, that's what you wanna do.
I just spent that whole time lost.
Do you want me to keep this up here?
Thank you. Just your note, your solution thing looks easier to understand now.
Okay, good, good. Okay, guys, we've got about a half hour left. I would like to turn the page a little bit, and I actually get very excited about this because derivatives, which we just covered in chapter 5, are fairly practical and fairly applied oriented. but I'm a theoretical mathematician. It turns out integration is much more theoretical in the way it's presented and the way it works. And so I actually enjoy it more than the differentiation, just personally. It's kind of my thing. So we're gonna start chapter 6 today. And this is the last chapter we're going to cover. I may go back, if I have time at the end of the semester, and do the L'Hopital's rule. There is a section on that in the book that I'm skipping as of now. I may go back to it, but it's mostly just, the only thing we would do there would be to prove L'Hopital's rule. The applications of it and solving the problems, you would have done that in your earlier calculus classes. So there would be nothing new for me to offer to you in that regard. So for now, I'm gonna skip by that so I make sure that I have time to cover integration. Integration really started like 200, 300 years BC. Archimedes was this Greek philosopher, mathematician. He was interested in finding areas of shapes and volumes of solids. So it's more than 2,000 years ago that this idea sort of was first developed. And it was only in the 1600s and 1700s when the fundamental theorem of calculus came along that it began to be associated with derivatives. So keep in mind, for most of the history of integration, it was not known that it had anything to do with differentiation. As we now know, it's extremely related to integration, to differentiation, because they are somehow opposite processes. So that's pretty cool that eventually that connection is made. And we get concepts like the fundamental theorem of calculus, antiderivatives, all of that kind of stuff. And for the last 200 or 300 years, people have been refining this idea of integration. Turns out there's different kinds of integration. There's Riemann integration, there's Lebesgue integration, and we are going to be focusing in 350 on Riemann integrals. Riemann integration, which is the same thing that you learn in your regular calculus classes. And also this idea was extended to discontinuous functions. We're going to find out that you don't have to have a continuous function to be able to integrate it. You can integrate things that have jumps and gaps and holes and all that kind of stuff. So that'll be a little bit of a difference compared with things like continuity, limits of functions that are continuous, which have to have limits at all points. So this is a little different in that regard. Now, whereas the definition of the derivative is super fast and super easy, I can't even define what an integral is for several more pages of my notes. It takes a little while to get there and to get it set up for us. And so we're going to jump in here into this first section and have to sort of do some preliminaries before I can actually define how integration works. Okay, but it's really cool. I love this. I love the way Riemann integration works and how it gets set up. And so let's get jumping into this with a definition. Okay. We're going to be considering, and this is definition 6.1, just for the book reference if you want it. Definition 6.1. By the way, there will be, of course, as always, a good dose of definitions to get your flashcards a workout as well. But I'm going to define what I mean by a partition of a closed interval. So I'm going to take a closed interval, let A be a closed interval. All right, so we do that. Obviously, A is less than B here. A partition, I'll denote this with P, capital P. A partition P of the interval AB is a finite set of points. So it's a set of points. I'll denote this as a set x0, x1, x2, and dot, dot, dot up to xn. So it's a finite set of points with n is just some natural number, has to be at least one. And the other thing about the partition is that the x0 value should be what A is. So A is equal to X naught, and then X naught is less than X1, is less than X2, and so on and so on. All the way to the other end, we have Xn, which is what is going to be equal to B. So this is the definition of a partition, and it's not anything too crazy. You just have your closed interval AB here. And a partition, guys, is just a way of chopping up this interval. So you've got X naught on this end, and you have X1, X2, X3, X4, and I'll say dot, dot, dot. The last one is Xn, and that coincides with B. So this is a partition. And you probably remember when you did integration back in calculus that you have to chop up when you're first defining how the Riemann sums work, you chop up your domain into little subintervals, and then you evaluate something, either the left-hand endpoint or the right-hand endpoint or whatever, and do some kind of a big summation. So we're gonna need this idea of a partition to really talk about this. Now, a related notation that I want to get everybody comfortable with right away is delta xi. And this is just going to be the width of the ith subinterval. So it would be, excuse me, xi minus xi minus 1. This would be for I equal to 1 or 2 or 3, dot, 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 up to n. Okay, so that is the width of the ith subinterval. So delta x1 would just be x1 minus x0, for example. That would just be the width of the first subinterval. x2 minus x1 would be delta x2, and so on. We got n of those. Obviously, if you add up all of the delta xi's, it should add up to the full width of the entire interval from A to B, which of course would be equal to what? The full interval has a width of B minus A, right, exactly. So the full width of the entire interval from A to B is B minus A, and if we add up all of these delta xi's, we would get that. We're gonna probably need that at some point, but just wanted to mention that. And then I have another notation for you, maybe I'll put it right here. For any given interval, if I take any interval, you can see that there would be gobs of partitions. There's not just one. There's so many billions of ways I could chop this up, right? So I need to create a set to collect all of the partitions into. I'm going to use a script P of AB to denote that. So script P of AB, or if the interval is sort of clear, I might just write script P. So sometimes you'll see me omit the interval if it's kind of obvious what the interval is. This denotes the set of all partitions of the interval AB, of which there's an uncountable number of them, right? It would just be some unimaginably large set. Huge, huge numbers of partitions. So that's just some notation to get us started. So far, so good? So far on the board here, we don't have a function yet. We just are talking about the x-axis and how we can chop it up and make partitions of intervals. That's all that's up here. But ultimately, of course, we're going to have a function that we want to integrate between A and B. That's kind of where we're going with this. So I need another definition to kind of start talking about the function. So this is the next definition, 6.2. And it turns out, well, for our purposes, we are going to let f, so f is going to be the function. We're going to let f not just be any old function, we're going to make it to be a bounded function. So let f be a bounded function on the closed interval AB. So f has a domain which is the closed interval AB, and it goes, of course, to the real numbers. But it's a bounded function. When I say that f is bounded, let me just recall what that means. That just means that the range of f, right, the outputs of f can be bounded on some part of the y-axis. Now, if you want to let your function go off to infinity or minus infinity, that's fine. Then what we're talking about is what's called an improper integral. And you would have studied those in calculus, but it would not have been the first thing you talked about, right? So that kind of comes later. For right now, I only want to talk about bounded functions, not improper integrals. Okay, so let's do this. Let's let P be a partition. So I'm going to chop up my interval AB according to x naught, x1, x2, and dot, dot, dot up to xn. This is an element of the partitions of A and B. The script P is the notation for the partitions. Okay, so then I haven't even made the definition yet. So far, just setting it up. What I'm going to do, guys, is I'm going to define capital M sub I. And I'm also going to be defining a little m sub I in a moment. We'll do them both kind of together here. And what capital M sub I is it is going to be the supremum of the f of x values just on that ith subinterval. So where x runs between xi minus 1 and xi, we're going to take just the f of x values on that subinterval, and the supremum of those values is what I'm going to call capital M sub I. What do you suppose the little m sub I is going to be? The infimum of the exact same set, exactly. This is the infimum of the set of the f of x's such that xi minus 1 is less than or equal to x is less than or equal to xi. And this would be for I equal to 1, 2, 3, up to n again. So those are just for each of my little subintervals. I can calculate capital M sub I and little m sub I. Right? So just to have a little visual on this, let me just draw a picture here. I don't want to make the picture too complicated. We start off at x naught. Maybe I have x1 here, x2 is here, and x3 is here. Let's just make a simple example to show. And we have some function like that. And what I'm talking about doing is on each one of these subintervals, I'm going to find the supremum and infimum values. So on this first subinterval, let me just put a little dotted line here. Also put one here. Right? I'm going to ask myself, where is the supremum value and where is the infimum value? So on the first subinterval, the highest point is right here. That's capital M1. And the little m1 would actually be right here on the endpoint of that subinterval. And then when we go from x1 to x2, we might notice that that little m1 is also the little m2. So the minimum or the infimum value on the second subinterval is right there at that left endpoint. And then this right here at the right hand endpoint would be capital M2. And then I also need to draw this in here. From the picture, the way I've got it, it looks to me like the capital M2 is also the little m3, and capital M3 is right there. Does this make sense? For each little subinterval, there's a supremum value and an infimum value. And so we have capital M's and little m's, one for each of the subintervals that we're looking at. Questions so far? Am I going too fast? Well, you can see why I want F to be bounded. If F wasn't bounded, then these supremums and infimums could be plus or minus infinity. The function has no upper limit or lower limit, it could be plus or minus infinity, and I don't want that, for at least for this initial conversation. I don't want to allow the capital M's or the little m's to be infinity. So let's add that into here as a remark. The remark is that since F is bounded, capital M sub I is an element of R, and little m sub I is an element of R for each I. So for every subinterval, the capital M and the little m will be real numbers. They will not be in the realm of infinity or minus infinity. Okay. And I'll just remind you briefly of the completeness axiom from way back in February, which basically said that if you take any subset of the real numbers, right, it has a supremum. So this capital M sub I is a well-defined expression. And then we proved as a sort of a proposition after that, that every non-empty subset would have an infimum as well. So that's what the capital M's and little m's are denoting here. Okay. Well, let's say I want to figure out the area under this curve. We can estimate it with a Riemann sum. And there's sort of two natural ways we can do that as of now. So far, there's two ways that we can do that. This is still part of the same definition. So I'm just gonna, maybe I'll make that clear here. Definition 6.2 continued. I'm now gonna define an upper sum and a lower sum. So here we go. The upper sum of F with respect to P is, okay, so the upper sum of F with respect to P, this is going to be written as U of P comma F. And what we're going to do is we're going to estimate the area under this curve by making rectangles whose widths are just going to be the widths of the subintervals and whose heights are going to be the capital M's, right? The upper sum is going to take advantage of these supremum values. So this is going to be a summation. You'll be seeing lots of summation notation in chapter 6. Summation as I goes from 1 to n of capital M sub I times delta x sub I. Okay, so this is the upper sum of F with respect to P. And similarly, you can add this one as well over here. Similarly, we have the lower sum. The lower sum of F with respect to P is my partition. The lower sum of F with respect to P is going to be denoted L of P comma F. This will also be a summation, I going from 1 to n of little m sub I times delta x I. This will be the so-called lower sum. Okay. So for a given partition, if I have a fixed partition, I can calculate its upper sum and or its lower sum. Obviously, this one the lower sum is going to be less than or equal to the upper sum. Because the little m's are always less than or equal to the big M's, since you're comparing infimums to supremums of the same sets here, you see. Right, and in fact, we can, let's just add, that's finally the end of the definition. Let me add, yeah, it's like a whole board, just to write all that notation down. That's all part of the definition. As a remark here, excuse me, if little m is less than or equal to f of x is less than or equal to capital M for all x in this closed interval AB. So if I sort of have, so in this context, I'm thinking, here's some big ceiling up here, capital M, and then down here somewhere is some floor, little m. Doesn't necessarily have to be the same as the big MIs or the little MIs. These are just lower and upper bounds for the entire function. Then we can actually point out that if we were to take little m times b minus a, so that would be to take the width of my so I'm only gonna make one rectangle. Its width is b minus a and its height is this tiny little m. That's gonna be less than or equal to L of PF. Because with the L of PF, your height of your rectangle could be higher than the little m. And at the same time, the lower sum is always less than or equal to the upper sum. So L of PF will always be less than or equal to UPF, and UPF in turn will be less than capital M times B minus A. And so thus what we can say is both L of PF and U of PF, they are both bounded. They are both bounded. There's an upper bound and then there's a lower bound, which is some fixed value, right? This is just a fixed number here. Little m is a fixed number, A and B are given, right? So same thing with capital M. So you've got sort of a smallest and a biggest value, a range of values here, and your upper and lower sums are always going to be dangling around in between those two bounds. With the lower one always less than or equal to the upper one for any given partition. Okay, so as you can see, I'll write it down just so we have a really thorough set of notes on this. But you can see that the lower sums are going to be underestimates of the actual area under the graph of the function, while the upper sums would be overestimates of the actual area, right? So for example, in this picture, the capital M1 would give me this much area, right? For that first rectangle. The second rectangle would look like this. And the third one would come up here. All of this shaded stuff that I'm doing in black here, all of that black shading is greater than the actual area under the graph. And you probably would have seen your calculus instructor show you a picture like that at some point. Right, so let's just write that down though, just for thoroughness in the notes. Another little remark here, which is that for each partition, so for each P element of script P, so for every partition in the set of all the partitions, U of P comma F overestimates the U of PF overestimates the actual area under the curve. The curve of f of x, that is. So the UPFs overestimate that value while the L of P comma F underestimates the L of PF underestimates the same area. Should probably put a little asterisk next to that remark. This is really not gonna make sense so much if the function is going positive, negative, positive, negative. You probably remember in calculus that, sometimes you have to subtract integrals. If you're trying to get an actual area, but your function is negative, then you have to do some kind of a sign changing along the way. So I'm not getting into all of that here. I'm just, this remark, let's just say it this way. If f of x is greater than or equal to 0 for all x in the interval AB. So we'll kind of limit the scope of this remark for now, so that it's mostly just addressing the case of a function that's greater than or equal to 0. Okay. All right, well, I am now ready to define. So all this preamble, but now I'm ready to actually define an integral. Don't have a lot of time, but I'm gonna at least get this down into the notes for now. Well, I'm ready for another definition. I don't know why I didn't explain which definition it is. Sorry. No, it's still part of definition 6.2. The definition that never ends. So again, the book's numbers, you don't need to know these. I'm just trying to give you a place to look. If you need to look at the book later to get the references on this. I'm just gonna define the upper and the lower Riemann integrals, and then we'll probably have to more or less call it a day. And we'll get to some examples probably next time. But let's define the upper Riemann integral. Riemann is R-I-E-M-A-N-N. Upper Riemann integral of f over the interval AB, closed interval AB. The upper Riemann integral of f, and by the way, as of now, the only assumption on f is that it's bounded. It doesn't have to be continuous, doesn't have to be differentiable, nothing like that. But it needs to be defined on this closed interval and just needs to be bounded. And what is it going to be? The notation for it is I'm going to write a little typical integral sign that you would have seen in your calculus courses. And to emphasize that this is an upper Riemann integral, I'm going to put an over line on top of it. So I put a line on top of this thing. And what this is, I'm going to take all of those upper sums, all of these guys. When I say all of them, I mean for every partition. I'm going to look at every partition. I'm going to compute all of those upper sums, each one of which overestimates the area under the curve. So if they're all giving me an overestimate, I better take the smallest of those overestimates. So that's going to be the infimum of all of the UPFs, such that P is in the set of partitions. So I calculate every possible upper sum, and I take the infimum of all of those values. Okay? And similarly, the lower Riemann integral of f. Last thing for today, guys. Lower Riemann integral of f over AB is, this one is written also with integral from a to b, but this time with an underlining. So instead of an overline, I'm going to put an underline on this one. I'm going to take all of those lower estimates, which are underestimates for the actual area, and I'm going to take the supremum. I'm going to take the supremum of all of those. So the supremum of all of the LPS, where P runs over all of the partitions of P. Okay, both of these exist in R. Okay, they are not going to be plus or minus infinity. How come? How come? Well, look at this, guys. All of your lower sums are at least this big. So and they're at most this big. The lower and upper sums are sort of sandwiched between these values. So your supremums and infimums are going to be sandwiched between those same values. They're not going to be blowing off to infinity or minus infinity. They're going to be real numbers. Your questions for me, I'm sure you're going to wonder about over the weekend is, how do these two things compare? Be nice if they were equal. Turns out they don't have to be equal, and we'll give examples of that next week. But when they are equal, that's when we're gonna say that our function is integrable. So I'll save that for the notes next week, but that's where we're heading with this. This is just kind of getting our feet wet. On Tuesday, I'll come in here and write down all this notation again. And that's gonna take a while. I better get here early. And we'll take it from there. So guys, that's it for today. Thank you so much. I will have office hours tonight if anybody wants to chat. Otherwise, have a great weekend.
Weekend.